This is some data from an experiment to look at the resistivity of a certain metal. So what we have is the resistance, which we can plot on the y-axis, and we've got the length of that wire plotted on the x-axis. Now when this was done, we measured values for the potential difference across that length of wire and the current through it. So the first thing we need to do is work out the resistance. So let's do this step by step. Of course, we know that R is equal to V over I. So all we need to do is take that value, 2.92, divided by 3.48, and then we get this number here. Now, they're both to three significant figures, so I'm going to give this to three significant figures, 0.839. We can do the same thing again for the next one, 2.91 divided by 2.03. But now we've got an answer, which is 1.43349, and to give this to three significant figures would now be 1.43. Now here, there's this kind of bit of ambiguity. Do you keep the same number of decimal places in your thing, or do you keep it to the same number of significant figures? I think it's probably best to do this to the same number of significant figures. And of course we can do that for the next few results as well. But now we've got 2.69 divided by 0.80. So we've used the same measuring instrument that measures, in this case, to two decimal places on that digital scale. But now we've got, I guess, raw data to two significant figures, and that's to three significant figures. So what should we give this to? I guess we could give it to two significant figures. We can justifiably say that. But what I'm going to do, so this one I'm going to write down as 3.36. So this is that kind of battle between significant figures and decimal places and what you keep consistent in your table. Also, realistically, we're going to be plotting this on a graph, and I don't think I could plot a data that precisely on my graph. So we can do the same for the last two bits of data, and we can now plot that data on a graph. And this is what it looks like. So we've got resistance in ohms and we've got length in meters, and we get a load of data like this. So we're going to draw in a line of best fit. And I would say that something that we're aiming for is going to be probably like that. There seems to be a slightly anomalous bit of data there, but I think for the rest of this data, that looks pretty good. Now, you will notice that this doesn't necessarily go through the origin, and sometimes that's because we get this systematic error as we're taking data. Maybe there's a kink in the wire, or maybe it's a little bit unsure about where the crocodile clips actually make that connection with the wire that we're measuring, which is why it doesn't necessarily go through the origin. So what we can now do, and maybe that line of best fit is slightly high because I've got quite a few points beneath it, but I think that's going to be good enough. We can now draw in some lines on here in order to work out the gradient. It's probably not my best line of best fit, but I think it's going to be good enough to kind of show you my approach to this question. If I was a teacher in class, I'd probably want you to be doing that again, rubbing it out and drawing it in, maybe just slightly more shallow. Anyway, let's just keep going as we are at the moment. So the gradient is the change in y by the change in x value. The change in y value goes from 5.0, and the value down here is 0.5 or 0.50, because we can see that's pretty good. We're going to divide that by the change in x value, which in this case, if that's 0.6, that's 0.7, so that's 0.75 take away 0.04. Okay, so I reckon that's a good data. So let's just work that out. So that's 4.5 divided by 0.71, which equals 6.338. Okay, and that's going to be ohms per meter. But we're trying to find the resistivity of that material. Now, looking at the equation here for resistivity, R is equal to rho over A times L. And on the graph, we've plotted R on the y-axis. On the x-axis, we've got L, which means the gradient is equal to rho divided by A. So if you want to find the value for the resistivity, rho, that's going to be equal to the gradient multiplied by the area of that wire. Now the area of the wire is going to be equal to pi d squared over 4. And in order to work out what that is, we've got the diameter here in three different places. So the area is going to be equal to the average of all of those three. So that's 0.33 plus 0.33 plus 0.31 divided by 3. We now need to convert that into millimetres. So I'm just going to divide by 1,000, and then we can square that, multiply by pi, divide by 4, to give an area equal to 8.21 times 10 to the minus 8 metres squared. So a very, very small area, but that's because it's a very, very thin piece of wire. So that means with this value for area and that value for the resistance per metre of wire, if we multiply the two things together, the resistivity is going to be this value, 8.31 times 10 to the minus 8, the area, multiplied by the gradient, which was 6.338. And this gives me a number equal to 5.2. And I think probably justifiably I could give this to two significant figures, probably like the raw data that I can actually read off my graph. Although I guess you could say, or you could argue it's 3. But I'm just going to say 5.2 times 10 to the minus 7. And because it's resistivity, the units are going to be ohm meters. And so 5.2 times 10 to the minus 7 ohm meters is an appropriate value for the resistivity of that metal that that wire was made out of. And this is a fairly standard procedure. You take a length of wire, you look at the potential difference across it and the current through it in order to work out its resistance. You plot the data like this, and then when you work out the gradient, you can then multiply that by the area to find out the resistivity. And just be aware that sometimes we often have a systematic error, maybe due to the connection at the start and end of that wire when it comes to measuring the length. So there we go, 5.2 times 10 to the minus 7.